In water, we constantly have a little of this going on. One water molecule donating a proton to another, yielding a hydronium ion and a hydroxide ion. There's a very small percentage of water molecules that this is occurring for at any one time, but it does happen, which means we could write an equilibrium constant expression for this reaction. Now you remember that an equilibrium constant expression has a K value, an equilibrium constant, and that's equal to products raised to their powers divided by reactants raised to their powers. Furthermore, we never write pure liquids or pure solids in an equilibrium constant expression, which means the equilibrium constant expression for the autoionization of water would look like this. Now typically, I'm going to shorten this to hydrogen ion times hydroxide ion concentration gives this number 1 times 10 to the negative 14th, but we recall that if we're counting hydroniums or we're counting hydrogens, the numbers are the same. So this equation is taken to be valid for pure water and for dilute aqueous solutions at 25 degrees Celsius. You recall that the value of the equilibrium constant depends on temperature. So the equilibrium constant for water, case of W, is not 1 times 10 to the negative 14th at some temperature other than 25 degrees Celsius. So for all problems, unless we're told otherwise, we're going to assume that the reaction is taking place at 25 degrees Celsius, and therefore Kw is equal to 1 times 10 to the negative 14th. If we have an acid or base, the balance between hydrogen ion and hydroxide ions is disrupted. For an acid, hydrogen exceeds hydroxide. For a base, hydroxide exceeds hydrogen. And, of course, for a neutral solution, the concentrations of hydrogen and hydroxide ions are the same. Let's try a problem. At 25 degrees Celsius, calculate the hydrogen ion concentration if the hydroxide ion concentration is 2.7 times 10 to the negative 4th molar. Is this solution an acid or base? So we're going to use the equation that was on the previous slide. Hydrogen ion concentration times hydroxide ion concentration equals 1 times 10 to the negative 14th. The hydroxide ion concentration is given as 2.7 times 10 to the negative 4th, so we can calculate the hydrogen ion concentration, which has the unit molarity, as 3.7 times 10 to the negative 11th. That was the first part of the problem. The last question is this solution an acid or a base? We look at the hydrogen ion concentration, particularly its power of 10. Hydrogen ion, 10 to the negative 11th. Hydroxide, 10 to the negative 4th, which is much larger than 10 to the negative 11th. In other words, there is more hydroxide ion than hydrogen ion. Therefore, this is a base. Let's summarize. In pure water, most particles are water molecules, but a few of these, for a short time, lose an H+. This donated H+ is immediately gained by a nearby water molecule, turning it, for a short time, into a hydronium ion. The water molecule that lost the proton becomes, for a short time, a hydroxide ion. There is thus a dynamic equilibrium set up between the H2O, H3O+, and OH- particles. And recall that we can count hydroniums as hydrogens, if we want. In pure water, the number of hydroniums, or hydrogens, equals the number of hydroxides. The balance is tipped if the solution becomes acidic, where hydrogen concentration exceeds hydroxide ion concentration, or basic, if hydrogen ion concentration is less than hydroxide ion concentration. For pure water and for dilute aqueous solutions at 25 degrees, the following equation holds. Essentially, hydrogen ion concentration times hydroxide ion concentration equals 1 times 10 to the negative 14th.